Okay, this video is about the focal length equation and how we can use it as another tool, just like light ray diagrams, to explain how various optical instruments work. So, we are mainly going to be in the problem set. In the light ray or ray diagram practice, we have lots of ray diagrams that you drew in the last few classes. But then next to it are all these numbers. And so today, in this video, we're going to be looking at all these numbers and specifically what they mean and how we can use them to relate to ray diagrams. So we've got two equations that we use when describing images. One of them is the mirror lens equation. It looks like this. Notice that everything is a denominator in terms of variables, and then everything is added. Well, by everything, I just mean those two things. So, DO is object distance, DI, image distance, F is focal length of the mirror. So, every mirror has a focal length. That is the distance between the mirror and the focal point. So whatever that distance is. It's usually given in centimeters. And when thinking about units for this, if all the units are the same, we don't need to convert. And I will always give you, and so will Quest, problems that are all the same unit. So if focal length is in centimeters, and so is image distance, and so is object distance, we don't need to convert. It's about these ratios between these numbers. So a couple calculator hints here. If you get a small decimal as a final answer for a distance, you forgot to do 1 divided by answer. And so this 1 divided by answer we will look at and practice, but the answer key is right here. And so what you do is you first press, if you look, the answer is blue, that little blue ANS. So that means second. So you have to press second first, then that minus symbol. And that's what this is talking about. Ask a friend or someone to show you in class if that's confusing for how we're getting that. So let's practice that equation using this as our example. So again, I'm going to write down the equation here. So we have a focal length. Notice it also gives us a center point of a mirror that's always twice as big as the focal length, and it gives me an object distance, and I'm trying to find my image distance. So I'm going to fill in those numbers over here. Now, to get this 1 divided by DI by itself, we need to subtract 1/6 to both sides. Now your calculator is pretty smart here, and it will allow you without parentheses to type that whole thing in there. So you should type in 1 divided by 4 minus 1 divided by 6, press enter. Now that number is not our final answer because that number equals, I'm not sure what it is, whatever it is right there, that number equals 1 divided by DI. So what we need to do is we have to do 1 divided by answer on your calculator. So you'll literally type in 1, then the divided by, then you're going to hit second, and then you're going to hit the minus sign. And it will show up like this. And what it means is the answer that you got previously. That should then give you a final answer that is not a decimal, but that is regular number like 10 or 8 or 12 or whatever it may be. It might have a decimal on there, but it's not like 0.1. And that's your DI right here. So whatever you get for your DI, you're going to put right in there. Now, in terms of height and magnification, we use a different equation. If we go back to our notes, we can take a look and see what that equation is. So let's first look at these new letters. M is magnification. There's no unit. And so if we get an M that is bigger, well, let's say our M is 1. Let's start there. That means that the object and the image are the same size. If M is greater than 1, then the image is bigger, or image is magnified, we could say. If M is less than 1, then the image is smaller. So like a convex mirror, for example. Let's say that the M is 2. That means the image is twice as big as the object. Let's say the M is 0.5. That means the image is half as big as the object. So that's M. H stands for heights. Height of image, height of object. And the D's are what we had before. Image distance, object's distance. Notice there's a negative here. The negative does not mean smaller. In fact, it usually aligns with inverted or upright. Not always. It can sometimes refer to a virtual image too. So negative usually means virtual, or it means inverted or upside down. And that kind of depends on each problem. Now, this equation is a little weird because there are 2 equal signs. So sometimes it's better to actually write this as 2 different equations. What the equal sign is trying to really say is, let's pretend that this didn't exist. Well, now it's saying that you have one formula that says magnification equals the image height over the object height. Now, the other way to write this is saying, let's pretend that this didn't exist. Well, now we're saying magnification equals negative di over do. And those are really the 2 equations that this magnification equation is saying and using. So, for the problem set, in order to solve for height, you have to solve for magnification first. Using your DO and your DI. Look at the key on the overview page. It will show you all the answers for all of these different problems. But know that first step in every problem is going to be going and finding that DI. Finding that DI. Do that first. Then go in and find the magnification, then the height. So first solve, second solve, third solve. It's like a puzzle. Can't solve one unless you know the others first. You have several questions all about this. A few hints on them is about sign rules for magnification and distances. So the main thing you can see in this picture over here, if a distance is in front of the mirror, it's positive. If it's behind the mirror, it's negative. So for a convex mirror, for example, they're always going to have negative numbers. Radius is a fancy way of saying mirror center or mirror center. So a convex mirror is going to have a negative center and a negative focus because it's behind the mirror, right? It's like this. Image distances will always, or sorry, object distances will always be positive. Image distances might change. Object heights will always be positive. Image heights might change. So this is kind of a helpful cheat sheet. And you can also look, because in your problems, when it comes to a convex mirror like this one, I've given you a negative focal length. Quest, however, won't, and it will just say some things like behind the mirror. And you need to know that behind the mirror is indicated by a negative mathematically. Just like velocity was negative or positive sometimes and talked about direction, these distances are negative, positive sometimes, and it's talking about location. So similar ideas. See the key on the overview page if you need more help and to check your work.